On the morning of February 27, 2026, a spacecraft more than 15 billion miles from Earth did something it was not supposed to do. Not dramatically. There was no alarm, no cascade of failures, no system going suddenly dark. What happened was smaller than that, and harder to manage because of it. During a routine planned roll maneuver, the kind Voyager 1 executes regularly to calibrate its magnetometer against the magnetic field of interstellar space, the power levels dropped. Not catastrophically. Not enough that anyone outside the operations team at NASA's Jet Propulsion Laboratory in Pasadena, California, would have noticed or known what to do with the information. But the team noticed. They noticed the way people notice things they have been watching for a long time and hoping would not arrive. The spacecraft runs on 3 radioisotope thermoelectric generators, canisters of plutonium-238 bolted to a boom extending from its body, each one converting the heat of slow radioactive decay into electricity. After 48 years in space, those generators produce roughly 200 watts of usable power. That number declines by approximately 4 watts every year, as the plutonium exhausts itself at the rate physics requires. There is no way to slow the rate. There is no way to add to the supply. The number goes in one direction only, and the team at JPL has spent the better part of a decade learning to live inside the shrinking space it defines. 200 watts sounds like enough. A standard incandescent bulb once drew 60. But 200 watts, divided across every system a spacecraft needs to stay alive, computers, transmitters, heaters, gyroscopes, science instruments, leaves a margin that has long since ceased to be comfortable. The team has been cutting for years. Heaters turned off. Instruments shut down in sequence, instrument by instrument, according to a plan they made in advance, because making it in advance was the only way to make it without panic. By the morning of February 27, there was very little left to cut. The spacecraft was running on what it needed, and not much more. When the power dropped during the roll maneuver, the margin that had been thin became something closer to critical. Not because the drop was large, because of what was waiting on the other side of another drop. Voyager 1 carries software called the Undervoltage Fault Protection System. It has been on the spacecraft since before it left Earth. Its job is to protect the mission from power failures by responding autonomously, shutting down components in a predetermined sequence to reduce the electrical load before the whole system collapses. In 1977, when the software was written, this was a reasonable design. A spacecraft operating near Jupiter, too far for real-time commands, needed the ability to protect itself without waiting for instructions from the ground. The response time from JPL to Jupiter was measured in tens of minutes. Fast enough that an autonomous response was a sensible backup, a safety feature designed to operate rarely and restore easily. Voyager 1 is not near Jupiter. It is 15 billion miles from Earth. A signal traveling at the speed of light takes 23 hours to reach it. A command sent from Pasadena arrives on the spacecraft nearly a full day after it was transmitted, and the confirmation that the command was received takes another 23 hours to come back. The round trip is 46 hours. In the context of that distance, the undervoltage protection system is not a backup. It is a problem. If the power levels on Voyager 1 fell far enough to trigger the fault protection, the system would begin shutting things down autonomously, not according to the team's carefully maintained priority list, not in the order the science team had spent years negotiating, but in the order it was programmed to follow in 1977, for a spacecraft near Saturn, by engineers who had no way to anticipate that the machine would still be running 48 years later in interstellar space. Recovery from a fault protection event is not impossible. The team has done it before. But recovery requires sending commands into a 46-hour communication void, working from simulators and models and documents that are not always complete, trying to undo a sequence of automated decisions made by software that is older than most of the engineers currently operating it. Each recovery attempt is a risk. Each one uses power the mission cannot afford to spend on emergencies. And each one leaves the spacecraft slightly more exposed than it was before. Karim Badarudin has been the mission manager for the Voyager interstellar mission. Before that, he spent 30 years at JPL as a supervisor of chief engineers, dividing his time between different flight projects, moving between missions as problems arose and were solved. When Suzanne Dodd, the Voyager project manager, needed someone to help manage the escalating technical challenges of an aging spacecraft, she looked for a chief engineer who understood that kind of work. Badarudin said she didn't need to look further. He described the moment of volunteering the way someone describes something they mean plainly, without performance. He said, "Look no further. I'm your engineer. Please pick me." He described the role as the best job at JPL. He said that too, the same way, directly, without decoration. He describes the fault protection system the way a person describes something they respect and do not want to need. The system is a safety net, he has said, and the trapeze artist should never let go of the trapeze. The safety net exists. It works. But catching the trapeze artist is not the same as the trapeze artist completing the routine. Fault protection puts the spacecraft in a safe state. Then the team has to get it back on the trapeze. And getting it back, from this distance, with this much of the mission already committed to keeping the essential systems running, is not a process anyone wants to initiate unnecessarily. On February 27, the power dropped. The team looked at the numbers. They understood what would happen if the power dropped again without intervention. And they understood what intervention meant, moving the list from the future tense into the present. The list was the plan they had made for this. Years before the February drop, before the power had thinned to the point where a routine maneuver could create a crisis, the Voyager science and engineering teams sat down together and worked out the order. Which instruments would go first? Which ones would be kept running longest? How to sequence the shutdowns so that the mission retained its scientific value for as long as possible, so that the things Voyager was uniquely positioned to measure in interstellar space kept being measured for every additional day the power allowed. The list was not made under pressure. It was made carefully, deliberately by people who understood both the physics of the power decline and the science of what would be lost at each step. By February 27, the list had already been partially executed. Several instruments had already gone dark. The team knew what was next. What the power drop did was remove the question of when. They did not wait for the undervoltage system to make the decision. They made it themselves. Not quickly, not without confirmation and simulation and rechecking, but faster than the mission's normal rhythm, because the alternative was ceding the decision to software that did not have the list, did not know the plan, and would not make the same choices the team would make given the choice. The instrument at the top of the list was the low-energy charged particles experiment, the LEC-P. It had been running on Voyager 1 since September 1977, nearly 49 years, almost without interruption. It measured ions, electrons, cosmic rays, the charged particles flowing through interstellar space from the solar system and from the galaxy beyond it. It had provided some of the clearest evidence that Voyager 1 had crossed the heliopause in 2012, detecting the shift in the particle environment that marked the boundary between the Sun's domain and everything else. It was, by any scientific measure, an instrument of extraordinary productivity. It had returned data nobody expected, from a place nobody had specifically planned to reach for far longer than anyone had designed it to last. On April 17, 2026, engineers at JPL sent the command to shut it down. The signal took 23 hours to reach the spacecraft. The shutdown process itself took 3 hours and 15 minutes to complete. By the time the confirmation arrived back at JPL, another 23 hours later, the instrument that had been running since 1977 was off. Most of it. One part remained, a small stepper motor that spins the sensor in a complete circle, giving it a 360-degree field of view. The motor draws half a watt. The team left it running, not out of sentiment, because leaving the motor running gives them the best chance of turning the instrument back on if the Big Bang works, and they find extra power. The motor does not know why it is still running. It just keeps spinning. In the dark, in the cold, at the edge of the solar system, waiting for a command that may or may not come. The sequence of commands to shut down the LEX-P, from the moment they were sent to the moment the shutdown completed and the confirmation returned to Pasadena, consumed the better part of 3 days. 46 hours of signal transit, 3 hours of execution, the time to verify the telemetry, to confirm the power readings had stabilized, to document what had changed. The mission did not pause during this time. The spacecraft kept moving, kept transmitting, kept listening for the next set of commands. The team kept working. The list moved forward by 1 line. That is what the end of this mission looks like from the inside. Not a dramatic failure. A list being executed, 1 line at a time, by a small team in Pasadena who drove to work that morning and will drive home that evening, and who are, in the space between, making decisions that cannot be undone about the farthest object humanity has ever touched. The list was not made in a hurry. It exists because someone, years before February 27, understood that the power decline was not a crisis that would arrive suddenly. It was arithmetic. 4 watts per year, every year, compounding not in the sense that the rate accelerates, but in the sense that each watt lost narrows the field of remaining options. And a narrowing field of options means that decisions made today eliminate possibilities that might have been useful tomorrow. The list was the team's attempt to get ahead of that arithmetic, to make the hard choices in a room with time to think, rather than in a room with an alarm going off. To understand what 4 watts per year means, it helps to start at the beginning. When Voyager 1 left Cape Canaveral on September 5, 1977, it carried 3 radioisotope thermoelectric generators mounted on a boom extending from the spacecraft's main body. Each one was a self-contained nuclear battery, a stack of plutonium-238 oxide pellets surrounded by thermocouples, devices that convert a temperature difference into electrical current. The hot side of each thermocouple sat against the fuel. The cold side faced the vacuum of space. The greater the difference in temperature between those 2 sides, the more electricity the system produced. At launch, the 3 generators together produced approximately 470 watts of electrical power. 470 watts. Enough to run a modest household appliance. Enough to keep 7 or 8 incandescent bulbs burning. In the context of what it had to power, 2 computers, a transmitter, a suite of scientific instruments, heaters maintaining temperature across a spacecraft the size of a small car. It was not lavish, but it was enough. The engineers who designed the system knew the number would decline. They planned for it. They built a mission that could be progressively scaled back as the power fell, keeping the most valuable systems running longest by shutting down the ones that had already served their purpose. Plutonium-238 has a half-life of 88 years. Every 88 years, half of the atoms in a given sample of it will have decayed, converted from plutonium into uranium-234, releasing energy in the process. The decay does not happen all at once. It happens continuously, atom by atom, at a rate that is absolutely fixed by the physics of the nucleus and that nothing in the universe can alter. No heater, no insulator, no engineering solution changes the rate at which plutonium-238 becomes uranium-234. The heat output of the generators has been declining since the moment they were fueled, and it will continue declining for centuries after the mission is over. After 48 years, at roughly 4 watts lost per year, the 3 generators that launched producing 470 watts now produce approximately 200. The math is not complicated. The consequences of the math are 200 watts, distributed across every system the spacecraft needs to function, leaves the mission operating at a power budget so constrained that a routine roll maneuver can create a crisis. The margin between operating and failing is now measured in single digits. Not hundreds of watts, not tens, single digits. The difference between a mission that continues and a mission that triggers its own fault protection system and begins shutting itself down is a handful of watts the team does not have and cannot obtain. Every 4 watts matters because every 4 watts is 1 year. That is the rate at which the options are closing. The team has been responding to that closure for decades. The earliest shutdowns were easy. Instruments designed for planetary flybys turned off after the flybys were complete, no longer collecting data that anyone needed from a region of space they had already left behind. The plasma science instrument on Voyager 1 went dark years ago, its performance too degraded to be worth the power it consumed. The shutdowns that came later were harder. These were instruments still producing unique data, still measuring things that could not be measured any other way, still returning information about a region of space that no other object had ever visited. Turning them off was not a technical decision. It was a scientific loss, made deliberately, because the alternative was a larger loss sooner. In October 2024, the plasma science instrument on Voyager 2 was turned off. It had been collecting only limited data in recent years, its orientation poorly matched to the direction plasma flows in interstellar space, but it had been running. It had been a system that was still on. After October 2024, it was not. On February 25, 2025, the cosmic ray subsystem on Voyager 1 went dark. A suite of telescopes designed to study high-energy particles, protons from the galaxy, particles from the Sun. It had been one of the instruments that helped the team determine, in 2012, that Voyager 1 had crossed the heliopause. It had been measuring the cosmic ray environment in interstellar space for years after that crossing, returning data about a place no instrument had ever measured before. Then it was off. On March 24, 2025, the low-energy charged particles instrument on Voyager 2 was shut down. The same instrument that would be shut down on Voyager 1 13 months later. The same rotating sensor platform, the same stepper motor, the same telescopes. On Voyager 2, by the time it went dark, the motor had completed more than 8.5 million steps. It had been tested on Earth to 250,000 steps, enough to guarantee operation through the Saturn flyby. What happened between that test and the shutdown is not a story about engineering margins. It is a story about the distance between a plan and what a plan becomes when the people executing it keep finding reasons to continue. The stepper motor is worth dwelling on, not because it is the most important component on the spacecraft, because it is the most precise measure of the gap between what was promised and what the mission became. 250,000 steps was the guarantee. That was the number the engineers committed to. That was what the testing established as sufficient for the mission as designed. A 4-year journey to Jupiter and Saturn, a flyby, and then, in the original plan, silence. The motor ran for 250,000 steps and kept running. It ran for 1 million steps and kept running. It ran through the crossing of the termination shock, through the approach to the heliopause, through the years in interstellar space that nobody had written into the original mission documents. By the time the instrument was shut down on Voyager 2, the motor had completed 8.5 million steps, 34 times the number it had been guaranteed to survive, and it was still functional when it stopped. Not worn out, not failed, stopped by a command from Earth to save the power it was drawing, because that power was needed elsewhere. On Voyager 1, the same motor ran until April 17, 2026, when it too received its shutdown command. By that point, it had also completed approximately 8.5 million steps. At negative 62 degrees Celsius, well below the temperature at which the supplemental heater keeping it warm had been turned off to save power, the motor kept stepping. Stamatios Kremigas, the instrument's principal investigator at the Johns Hopkins Applied Physics Laboratory, wrote afterward that the stepper had worked flawlessly for nearly 49 years and over 8.5 million steps. He described it as the stuff that dreams are made of. He said it without irony, because there was no irony available. The instrument worked perfectly until the moment it was turned off. It was turned off not because it failed, but because the power it consumed was more valuable than the data it produced. And that calculation was the entire mission now. When the LECP went dark on Voyager 1 in April 2026, the spacecraft was left with two operating science instruments: the plasma wave subsystem, an antenna that listens to oscillations in the plasma of interstellar space, converting them into data that describes the density and structure of the medium the spacecraft is moving through, and the magnetometer, a sensor measuring the direction and strength of the magnetic field in the space beyond the heliosphere. Two instruments, both still working, both still sending data from a region of space that no other human-made object has ever reached. The power they consume is not large. The magnetometer draws very little. The plasma wave subsystem draws a modest amount. But modest amounts are no longer the unit of accounting that matters. What matters is the total power available against the total power required, and the margin between them, and the rate at which that margin continues to shrink. 4 watts per year. Every year. Without exception. The mission will not stop because an instrument fails. It will stop because the arithmetic catches up to the last instrument standing. The team knows the order. They made the list. They know which of the 2 remaining instruments is likely to go next, and roughly when, and what will be left after that. They know, within the tolerance of their thermal and power models, how many more winters this spacecraft has. Though winter is not a concept that applies at 15 billion miles from the sun, where the temperature of space itself hovers just above absolute zero, and has been that way for the entire mission. There are no seasons out there. There is only the slow, fixed, unalterable rate of decay, and the team's increasingly narrow ability to stay ahead of it. Patrick Cohn, the Voyager program scientist at NASA headquarters in Washington, said after the 2025 shutdowns that every bit of additional data gathered since the planetary flybys ended was not only valuable bonus science, but also a testament to the engineering that has gone into the Voyagers since nearly 50 years ago, and continuing to this day. The statement is accurate. It is also the kind of statement that can obscure what is actually happening if you let it. The testament is real. So is the list. Both things are true, and the list is the part nobody frames on the wall. Linda Spilker, the Voyager project scientist at JPL, said something that sits differently. She said that every minute of every day, the Voyagers explore a region where no spacecraft has gone before. And that also means every day could be our last. But that every day could also bring another interstellar revelation. She said both of those things, the last and the revelation. She did not resolve the tension between them, because the tension between them is not resolvable. It is the operating condition. The mission exists in that tension, has existed in it for years, and will continue to exist in it until the list runs out. 2 instruments, 200 watts, give or take, declining by 4 watts per year. A team in Pasadena working the problem every day, driving in the morning, driving home in the evening, in between making decisions that will still be true 46 hours from now when the confirmation arrives. The list moves forward, 1 line at a time. Voyager 1 was designed to last 5 years. That is not a figure of speech or a conservative estimate that everyone privately assumed would be exceeded. It was the mission. Jupiter and Saturn. A gravity-assisted trajectory that would carry the spacecraft past the 2 largest planets in the solar system, collect data during the flybys, and then go quiet. 5 years was not a minimum. It was the plan. The spacecraft was built to execute that plan and no other, and the engineers who built it were not being unimaginative. They were being precise. They had a trajectory, a set of scientific objectives, a power budget, and a timeline. The timeline was 5 years. Everything on the spacecraft was sized for that timeline. The instruments were sized for it. The heaters that kept the electronics warm were sized for it. The software was written for it. The documentation, the technical manuals, the command dictionaries, the fault protection specifications, the wiring diagrams, the memoranda describing what each software routine does and why, was produced for a 5-year mission to the outer planets, and then, in the manner of documentation everywhere, was not fully updated as the mission became something else. That last part is where the story starts to carry weight the headline version does not. When people talk about Voyager's longevity, 48 years and still transmitting, the farthest human-made object, the first spacecraft in interstellar space. The framing is almost always one of wonder. And the wonder is real. The engineering that made it possible is genuinely extraordinary. The people who have kept the mission running through decades of declining power and escalating distance deserve every bit of the credit they receive. But the wonder tends to flatten something that the engineers themselves do not have the luxury of flattening, which is this. Every year the mission continues is another year the team is operating a spacecraft using documentation that is 1 year more out of date, managing systems that are 1 year further from their tested conditions, making decisions about hardware and software that was not designed to be in the state it is currently in. The documentation problem is not a complaint. It is a physical condition of the mission, the same way the power decline is a physical condition. It cannot be fixed. The original engineers who wrote the manuals are mostly gone, retired, no longer reachable, or in some cases no longer alive. What they left behind is what exists. Technical documents typed on typewriters in the 1970s, with revisions added in different hands at different times, not always consistently, not always completely. There are documents that describe the software as it was written. There are fewer documents that describe the software as it was subsequently modified, because modifications made across decades of operations do not always generate comprehensive new documentation. They generate notes, memos, changes logged in formats that made sense at the time. Badarudin has described the situation in terms that are precise without being alarming, which is the only way to describe it if you are the person responsible for managing it. The team feels really good about the hardware, he has said. They know exactly what the circuitry is, what the computers are, where the software runs. The hardware is well understood. The software is harder. There have been so many tweaks and changes over the years that working out the exact revision of every part of Voyager's code is complicated. And the practical solution the team uses when they need to know exactly what is running on the spacecraft is to request a memory readout directly from Voyager 1. A memory readout from a spacecraft 15 billion miles away. The request goes out, travels for 23 hours at the speed of light, arrives at the spacecraft, triggers a transmission of the current contents of the flight computer's memory, and that transmission travels back to Earth for another 23 hours before anyone in Pasadena can read what it says. 46 hours to find out what software version a system is running, not because the team is poorly organized, because there is no other way to be certain. That is not a remarkable fact in the way that mission milestones are remarkable. It does not inspire the same response as learning that Voyager has crossed into interstellar space, or that its signal still reaches Earth after 48 years. But it is the fact that changes the shape of every other fact, once it is understood. Because what it means is that every command sent to the spacecraft, every modification made to its behavior, every attempt to squeeze additional power or additional life out of systems that have been running since 1977, all of it is being done in partial darkness, not total darkness. The team is extraordinarily competent and has built simulators, hardware models, and analytical tools that give them a very high degree of confidence in their understanding of the spacecraft. But the simulators model the hardware as it was. The spacecraft is the hardware as it is, after 48 years of radiation exposure, thermal cycling, component aging, and accumulated software modification. The gap between those two things is not large. But at this distance, at this stage of the mission, not large is not the same as absent. In late 2024, the team attempted something that illustrated this gap directly. There are junction field effect transistors in a particular circuit on Voyager 1, electronic components that had become degraded over decades of radiation exposure in interstellar space, where the heliosphere's protective magnetic field no longer shields the spacecraft. The degradation was affecting performance. The team knew from materials science that transistors of this type can sometimes be healed by annealing, by heating them to a high enough temperature for long enough that the crystal structure of the semiconductor partially repairs itself. They had what they believed was enough power margin, They ran the heater. The power demand exceeded what the system could supply. The undervoltage fault protection triggered. The heater meant to heal the transistors was cut off. The transistors were not healed. And when the undervoltage protection responded, it did what it was designed to do. It turned off the X-band transmitter, the primary high-frequency link used for all normal science data, and switched to the S-band transmitter instead. The S-band uses less power. Near Earth, near the Moon, it is a functional communications link. At 15 billion miles, the S-band signal arrives too faint to carry data. What it carries is a carrier signal, a bare electromagnetic presence, just a frequency, no content. The team in Pasadena could detect it. By detecting it, they could confirm the spacecraft was still transmitting, still pointing its antenna at Earth, still alive, even before any telemetry came through. The S-band signal told them the spacecraft had survived the fault protection event. It told them nothing else. They had to wait for the X-band to come back online to find out what had actually happened. Badaruddan's summary of the annealing attempt is exact. The problem is still there. They realize they cannot solve it this way, and they are going to have to come up with another creative solution. That is the operating condition. That is what it means to manage a spacecraft in its 48th year using documentation from its first. You run an intelligent experiment based on real materials science, with real power margin calculations that the models support. And the spacecraft does something the model did not predict, and the problem you were trying to fix is still there, and now you need another idea. The 2023 anomaly was different in kind but similar in its demand for improvisation under constraint. Voyager 1 began transmitting meaningless data, a stream that corresponded to no recognizable telemetry format. The team eventually traced the problem to a single failed integrated circuit in the flight data system, a component responsible for packaging science and engineering data before transmission. The circuit was not repairable. The code that ran through it had to be relocated, moved around the failed area the way a road is rerouted around a collapsed bridge. The relocation required writing new software for a system running code from the 1970s, then transmitting that software to a spacecraft 15 billion miles away and waiting 46 hours to learn whether it had loaded correctly. The code was compact. There was no free space the team could take advantage of. They had to sacrifice something. What they sacrificed was one of Voyager 1's higher data rate modes, a transmission speed used during planetary flybys that the spacecraft no longer needed. But that was gone now regardless. A capability traded for a fix that worked, and a spacecraft that came back from a failure that had, for several months, left the team unable to read any coherent data from the farthest object humanity has ever built. All of this, the annealing attempt, the circuit failure, the software relocation, happened before February 27, 2026. Before the power drop during the roll maneuver. Before the LECP shut down. The February drop was not the beginning of a crisis. It was one event in a mission that has been managing escalating crises for years, getting better at it through forced practice, finding solutions in the space between what the documentation says and what the spacecraft actually is. In August 2012, Voyager 1 crossed the heliopause. The heliopause is the boundary where the sun's magnetic field and solar wind give way to the interstellar medium, the thin, cold plasma that fills the space between stars. Inside the heliopause, the environment is dominated by the sun, its particles, its field, its influence on everything within its reach. Outside the heliopause, the sun is just another star. Its magnetic field is no longer the organizing principle of the local environment. What exists out there is what the galaxy itself provides. Cosmic rays from distant supernovae, magnetic fields shaped by processes that have nothing to do with the solar system, plasma whose density and composition reflect conditions across thousands of light years rather than the 8 light-minute sphere of the sun's direct domain. Nobody wrote a mission document for that environment. The instruments still running on Voyager 1 in 2012 were designed and calibrated for conditions much closer to home. The data they returned from interstellar space was therefore simultaneously more valuable than anything the original mission planners expected to gather, and more difficult to interpret than data collected in a well-characterized environment. More valuable because no instrument had ever measured the interstellar medium in situ, only modeled it from Earth, inferred it from the behavior of distant phenomena. More difficult because the instruments were operating outside their calibrated range, in conditions nobody had validated them against. The team adapted. The science team developed new interpretive frameworks. The engineering team found ways to keep the instruments running in an environment that subjected the spacecraft to radiation the heliosphere had previously blocked. The mission that nobody had written into the original documents became a mission that produced some of the most significant scientific data in the history of space exploration: direct measurements of interstellar space, of the structure of the heliopause, of the particle environment beyond the Sun's influence. But the crossing of the heliopause also made permanent something that had been building for years. After 2012, there was no version of the Voyager mission that matched the original plan. The spacecraft was in a place the documentation did not cover, doing science the original instruments were not designed to do, running software that had been modified so many times that the reliable way to know what version was running was to pull a memory readout and wait 2 days. The gap between the mission as planned and the mission as lived became, after 2012, a permanent operating condition rather than a temporary deviation. The people managing the mission after 2012 were not managing the mission that was designed. They were managing whatever the mission had become, an improvisation sustained across decades by competence and ingenuity, and the slow, careful attention of a small team who understood that every decision now had to be right on the first attempt. Because at this distance, at this power level, with this much already committed, there was no reliable way to take one back. That understanding that the first attempt has to work runs underneath every subsequent decision the team makes. The LEC shut down in April 2026. The Big Bang maneuver being planned for the summer. The thruster reconfiguration already executed. The software modifications written for hardware that the original documentation does not fully describe. Each one is a first attempt. Each one is sent into a 46-hour void. Each one arrives at a spacecraft that will either respond correctly or will not, and there will be 23 hours of silence before anyone in Pasadena knows which. The mission crossed the heliopause in August 2012. The team adapted. They kept going. They are still going. The documentation does not cover where they are. It has not covered where they are for more than a decade. And the spacecraft keeps moving deeper into a region the documents were never written to describe. The heliopause is not a wall. That distinction matters more than it might seem. A wall implies a surface, a place where one thing ends and another begins, abruptly, with a clear before and after. The heliopause is not that. It is a boundary in the sense that a coastline is a boundary, real, mappable in general terms, but irregular at close range, responsive to conditions on both sides, shifting slightly depending on the solar wind pressure and the density of the interstellar medium pressing back against it. When Voyager 1 crossed it in August 2012, the crossing was not a single moment. It was a region, traversed over weeks, during which the instruments registered a shift in the particle environment that was gradual enough to require analysis before anyone was confident about what it meant. The team knew something had changed. The cosmic ray subsystem began registering a sharp increase in galactic cosmic rays, high-energy particles from outside the solar system that the heliosphere's magnetic field had previously deflected. At the same time, the low-energy particles associated with the solar wind dropped dramatically. The two changes together were the signature the scientists had predicted would mark the crossing. But the crossing also produced something unexpected. The magnetic field direction did not change the way the models had predicted it would. The models had suggested that the interstellar magnetic field would be oriented differently from the heliospheric field. The measurements showed it was not. The boundary region was stranger, and more complex than the predictions. The data that came back from the crossing did not simply confirm the models. It revised them. That is the specific thing Voyager does that nothing else can do. Not confirm what is already understood. Arrive somewhere the models have been describing from a distance, measure it directly, and return data that forces the models to change. The plasma wave subsystem on Voyager 1, one of the two instruments still running as of April 2026, has been listening to the interstellar medium since the crossing. What it hears is oscillations in the plasma, waves moving through the electrically charged gas that fills the space between stars. These oscillations carry information about the density of the medium, about the pressure fronts that move through it, about the way disturbances propagate across a region of space that extends for light years in every direction. When a large solar storm drives a burst of energetic particles outward from the Sun, those particles eventually cross the heliopause and send a pressure wave through the interstellar medium. The plasma wave subsystem can detect that wave. It detected one in 2012, another in 2014, and others in subsequent years. Each detection allowed the team to measure the local density of the interstellar medium directly, not inferred, not modeled, but measured, from inside the medium itself. The density of the interstellar medium is not a trivial number. It is one of the inputs into models of how the galaxy works, how cosmic rays propagate between stars, how stellar winds interact with the interstellar environment, how the Sun's heliosphere is shaped by the pressure of the medium it is moving through. Before Voyager, these models were built on indirect measurements and theoretical constraints. After Voyager, they have direct data from a single point inside the medium. One point, the only point any human instrument has ever occupied in that region. The magnetometer, the other surviving instrument, measures something complementary. Magnetic fields in interstellar space are not generated by the Sun. They are the remnant fields of ancient stellar events, supernovae, stellar winds, the slow turbulent stirring of the interstellar medium over billions of years. The field at Voyager 1's current location reflects the local magnetic environment of the Milky Way galaxy in a small patch of space roughly 15 billion miles from the Sun. That number, 15 billion miles, sounds vast. It is, from a human perspective, incomprehensibly large. From the perspective of the galaxy, it is nothing. The nearest star to the Sun is approximately 25 trillion miles away. Voyager 1 has covered less than 1% of that distance in 48 years. The magnetometer data from that fraction of the journey has already revised scientific understanding of the structure of the heliospheric boundary and the local interstellar magnetic field. The remaining distance, the overwhelming majority of the journey to the nearest star that Voyager will never complete, will not be measured by any instrument currently in existence or currently planned. There is no follow-on mission. There is no replacement instrument. The data that Voyager 1's magnetometer collects today and tomorrow, and for however many more days the power allows, is data that will not be collected again by anything built by human hands for a very long time, if ever. This is the fact that the shutdown sequence makes concrete in a way that abstract descriptions of scientific value do not. When the magnetometer goes dark, whether in 2027 or 2028, or sometime after that, depending on how the power budget evolves and whether the Big Bang maneuver succeeds, the measurement stops. Not temporarily, not until a replacement can be positioned, permanently, on any timescale that is meaningful to the people currently alive. The interstellar medium at Voyager 1's location will continue to exist. The magnetic fields will continue to fluctuate. The plasma will continue to oscillate. None of it will be heard. The plasma wave subsystem will most likely go first. It draws more power than the magnetometer. When the team has to choose between them, the magnetometer's lower power consumption makes it the instrument more likely to be kept running longest. But that calculation is not yet final. The Big Bang maneuver, if it works, may change the arithmetic. The team has not given up on either instrument. They are not in the business of giving up before the arithmetic requires it. What the plasma wave subsystem has been returning from interstellar space is data that has no terrestrial equivalent and no prior reference point. The oscillations it measures are not like anything the instrument was designed to listen to near the planets. Near Jupiter, the plasma wave subsystem listened to the electromagnetic environment of a giant magnetosphere, the radio emissions of a world 10 times the size of Earth, the crackling of lightning in an atmosphere of hydrogen and helium. In interstellar space, the instrument listens to something quieter, and in some ways stranger, the low hum of a medium that extends across the galaxy, disturbed periodically by pressure waves from a sun that is now so far away its influence arrives as a secondary effect rather than the dominant one. The team converts those oscillations into audio files sometimes, mapping the frequencies into the range human ears can detect, and the result is something that sounds, imprecisely but recognizably, like a sustained tone, rising and falling slightly with the density variations in the plasma, carrying information about a physical environment that no human sense was designed to perceive directly. The instrument is not making music, it is making data. But the data, translated into sound, has a quality that is difficult to describe without reaching for language that the instrument itself would not recognize. It is what interstellar space sounds like, rendered in a format a human nervous system can register, from a machine that has been running for 48 years against all reasonable expectation. That instrument is drawing power right now. It will continue drawing power until the power available falls below the level required to operate it. When that happens, the tone will stop. Not fade. Stop. The instrument will either be commanded off deliberately, in accordance with the list, or the power will drop below the threshold and the undervoltage protection will cut it. And in either case the result is the same. The plasma wave subsystem will stop listening. The data stream will end. The medium it was measuring will not change. The galaxy will continue doing what the galaxy does. The instrument will simply no longer be there to record it. The signal carrying that data travels from Voyager 1 to Earth at the speed of light, 186,000 miles per second, the fastest anything in the universe moves. At that speed, crossing 15 billion miles takes 23 hours. The photons that carry Voyager's transmissions leave the spacecraft's antenna and travel for nearly a full day before they reach the 70-meter dishes of the Deep Space Network and are captured, amplified, and decoded. What arrives is almost nothing. The transmitted signal leaves the spacecraft at 23 watts, less than a standard light bulb, spread across the surface of an expanding sphere that grows larger with every passing second of the signal's journey. By the time that sphere has expanded to 15 billion miles in radius, its surface area is so vast that the fraction of the original signal power intersecting the antenna of a Deep Space Network dish is less than 1/trillionth of a watt. The signal that arrives is not faint in the way a distant radio station is faint. It is faint in a way that requires some of the most sensitive receiving equipment on Earth to detect it all, equipment designed specifically for this purpose, upgraded repeatedly to maintain sensitivity as the spacecraft has moved farther away. The Deep Space Network dishes located in California's Mojave Desert, near Madrid in Spain, and outside Canberra in Australia, are the only instruments on Earth capable of maintaining a reliable link with Voyager 1. The three-site distribution ensures that at least one dish is always positioned to face the spacecraft as Earth rotates. Because the spacecraft does not wait for Earth to turn, it transmits continuously. The network listens continuously. The link between Voyager 1 and the ground is a thread of electromagnetism thinner than anything the word thin usually describes, sustained by the physics of focused transmission and sensitive reception across a distance that no communication link has previously been asked to span. That thread is what the power decline is attacking. Not directly, the transmitter itself is one of the last systems the team will shut down. Because without the transmitter there is no mission at all, regardless of how many instruments are still running. But the power available to the transmitter is drawn from the same generators that power everything else, and as the total available power declines, The team's ability to keep the transmitter operating at full capability becomes part of the same calculation as everything else. The transmitter is not going to be shut down to save power, but the systems that support it, heaters, backup components, the flight computer cycles allocated to managing the communication link, are all subject to the same arithmetic. Everything is. The data that arrives from Voyager 1 carries information about a place the signal took 23 hours to leave. By the time the data lands at a dish in the Mojave Desert and is routed to the operations team in Pasadena, the spacecraft has already moved. It has been moving at approximately 38,000 miles per hour since 1977. In the 23 hours the signal was traveling, the spacecraft traveled roughly 870,000 miles further from Earth. The data describes conditions at a location the spacecraft no longer occupies. The spacecraft is always ahead of its own signal. It is always already somewhere else. That is not a poetic observation, it is a logistical one. When the team receives data indicating a problem, a power fluctuation, an anomalous reading, a change in the spacecraft's behavior, the problem has already been happening for 23 hours by the time anyone knows about it. The response takes another 23 hours to arrive. The spacecraft will have been alone with the problem for 46 hours before any human intervention is possible. In that window, it relies on its own systems, its own fault protection software, its own ability to keep itself alive without guidance. And the older the spacecraft gets, the more its own systems are the thing it most needs guidance about. The signal that arrives from Voyager 1 is less than 1/1,000,000th of a watt. It has traveled for 23 hours. It describes a place the spacecraft left behind while the signal was in transit. It is the thinnest possible thread of connection between a machine at the edge of the solar system and the people in Pasadena responsible for keeping it running. And it is right now, still arriving, still carrying data, still telling the team what the plasma wave subsystem heard and what the magnetometer measured, in a region of space no instrument has previously occupied. The spacecraft will keep transmitting as long as the power allows. By the time the last signal arrives, it will already be describing the past. The Big Bang is what the team calls it, and the name is not entirely a joke. The nickname comes from the nature of the maneuver itself, not a gradual adjustment, not a single instrument shutdown, not the kind of incremental power management the team has been performing for years. The Big Bang is a simultaneous swap, a coordinated, all-at-once reconfiguration of multiple powered systems across the spacecraft, turning some things off and replacing them with lower power alternatives, designed to free up enough electrical headroom that the mission can continue operating its remaining science instruments for significantly longer than the current trajectory allows. The team has been planning it for months. It is the most complex engineering operation the Voyager mission has attempted in years, possibly ever, and it will be executed from a desk in Pasadena, sent into a communication void, and either succeed or fail before anyone in California knows which. The pressure behind it is not just the power decline. The power decline is the clock everyone can see. There is a second clock running in parallel that gets less attention but that the team thinks about every day. The thrusters. Voyager 1 fires its thrusters approximately 40 times per day. Not for propulsion. The spacecraft stopped accelerating toward any destination a long time ago, and at 38,000 miles per hour it will continue on its current trajectory, without any thrust at all for as long as the solar system exists. The thrusters fire for attitude control. Small corrections to the spacecraft's orientation, keeping the high-gain antenna pointed toward Earth within the precise angular tolerance required to maintain the communication link. Without those corrections, the antenna drifts. A drift of more than a fraction of a degree, at a distance of 15 billion miles, is enough to lose the signal entirely. The thrusters are not optional. They are the mechanism that keeps the thread connected. The problem is what is happening inside them. The fuel tanks on Voyager 1 contain hydrazine, a liquid propellant that ignites on contact with a catalyst inside the thruster. The tanks have rubber diaphragms inside them. bladders that separate the hydrazine from the pressurized gas used to push the fuel toward the thrusters. After 48 years, silicon from those rubber diaphragms has begun to leach into the hydrazine. Silicon does not ignite the way hydrazine does. When a tiny amount of silicon-contaminated hydrazine flows through a thruster and is burned, the silicon does not combust. It deposits, a microscopic residue left behind in the thruster capillaries, the narrow internal passages through which the fuel flows before reaching the combustion zone. Each firing leaves a trace. Each trace is slightly larger than nothing. Over 48 years of 40 firings per day, the traces accumulate. The capillaries narrow. The flow of fuel through the thruster becomes marginally more restricted with each passing month. Bata Rudin uses the analogy of clogging arteries, and the analogy is precise in the way that good analogies are, not decorative, but structural. The thrusters are not failing. They are gradually, incrementally, mechanically losing the ability to do their job, and the rate of that loss is not fixed in the way that the rich power decline is fixed. It depends on how much the thrusters fire, how contaminated the fuel has become, how the deposits distribute themselves across the thruster branches. Each thruster has 3 branches, parallel pathways through which the fuel can flow to reach the combustion zone. The 3 branches do not clog at the same rate, because small variations in manufacturing and in the distribution of silicon contamination mean each one ages slightly differently. The current software that controls the thrusters operates on the assumption that a given branch will be used for all attitude corrections in a given axis. The software does not mix branches. It picks one and uses it consistently. But what if one branch of the pitch thruster is in better condition than the corresponding branch of the yaw thruster? What if the optimal configuration requires mixing, branch 2 for pitch and branch 3 for yaw, a mode of operation that the current software does not support? That is the solution the team has been working toward. A software modification that would allow the thrusters to operate in mixed mode, selecting the least clogged branch for each axis independently, rather than being locked into a consistent branch assignment that treats all thrusters as equivalent when they are demonstrably not. The modification is not simple. The thruster control software is part of the same codebase that has been accumulating patches and revisions since 1977. Writing a new modification means understanding the existing code well enough to add to it without breaking anything else, on a system where the code is compact, where there is no free space to work in without sacrificing something, and where the only way to test the result with certainty is to send it to the spacecraft and wait 46 hours to find out whether it worked. The thruster clock and the power clock are related in a way that is not immediately obvious but becomes clear when you follow the logic. If the thrusters clog to the point where they can no longer maintain the spacecraft's attitude, the antenna drifts off Earth. If the antenna drifts off Earth, the communication link is broken. A broken communication link means no commands can be sent, no power management, no instrument control, no software updates, no Big Bang. The thruster failure mode does not wait for the power to run out. It is a separate path to the same end, running on its own timeline that the team cannot calculate with the same precision as the read-EG decay. What makes this more immediate is what the team already accomplished with the thrusters in 2025. A set of backup thrusters on Voyager 1 had been considered unusable for 21 years, dormant since 2004, written off, not part of the operating plan. In early 2025, before a planned communications blackout caused by maintenance on the Deep Space Network's antenna infrastructure, the team revived them. They fired successfully. 21 years of dormancy in interstellar space, and they fired. The team now has those thrusters back in the operational rotation, alternating with the primary thrusters to distribute wear and slow the rate of silicon accumulation in any single set of capillaries. The revival was not sentimental, it was practical. Every additional set of thrusters in rotation is additional time before any one set clogs to the point of failure. The Big Bang maneuver, if it works, addresses the power problem. The thruster software modification addresses the clogging problem. 2 engineering efforts, simultaneously on a spacecraft whose documentation is incomplete, whose code is compact and heavily patched, whose responses to commands take 46 hours to confirm. The engineers doing this work are not doing only this work. They are, as Badarudin has described the team generally, dividing their time between Voyager and other flight projects, because the mission does not have the staffing it had during the planetary encounters. It has what it has. The people it has are doing what they can. The Big Bang involves a specific set of trades. Powered devices that draw relatively large amounts of current will be turned off. In their place, alternative systems drawing less current will be activated. Some of the power freed by the shutdowns will go to maintaining the temperatures the spacecraft needs to keep its fuel lines from freezing, because if the hydrazine freezes, the thrusters cannot fire, and if the thrusters cannot fire, the antenna drifts, and the mission ends on that day regardless of what the power budget looks like. Some of the freed power will go to the remaining science instruments, extending the time they can continue operating. And if the swap goes exactly as planned, there is even a possibility that the LECP on Voyager 1 shut down in April 2026. Its stepper motor, still spinning on half a watt, could be switched back on. Not because the instrument is essential to the minimum mission, because the team has a motor still running, and an instrument that was working perfectly when it was turned off. And if the power allows it, returning that instrument to operation means more science from a place no science has previously been done. The team will attempt the Big Bang on Voyager 2 first. Voyager 2 has a slightly larger power margin than Voyager 1, not much, but enough to provide a small additional buffer against the possibility that the swap does not go exactly as planned. Voyager 2 is also closer to Earth, roughly 13 billion miles against Voyager 1's 15 billion, which means the round-trip communication time is about 38 hours rather than 46. 8 hours is not a large difference in the context of a mission measured in decades, but in the context of managing an emergency response to a failed procedure on a spacecraft in the final stage of its mission, 8 hours can matter. The results on Voyager 2 will be fully understood before the same procedure is attempted on Voyager 1. Tests on Voyager 2 are planned for May and June 2026. If they go well, if the swap behaves as the simulations predict, if the power budget stabilizes at the expected levels, if the thermal models hold, the team will attempt the same procedure on Voyager 1 no sooner than July 2026. The phrase "no sooner than" is deliberate. The team will not rush the Voyager 1 attempt before they have fully understood what Voyager 2 produced. The simulations are good. The models are good. But the annealing attempt had good simulations and good models, and the power demand still exceeded what the system could supply. The models are not the spacecraft. The spacecraft is 48 years old and has been in interstellar space for more than a decade and has accumulated experience that no model fully captures. The commands will be sent from Pasadena. They will travel for 23 hours. They will arrive at the spacecraft, and the spacecraft will begin executing them. For a period during the procedure, the spacecraft will be in a transitional state between the old configuration and the new one, where its behavior is not identical to either the state the simulators model or the state the team has been managing. That transitional period is the risk, not because the team expects it to produce a problem, but because a problem during a transitional state, at this distance, with this communication delay, would be the hardest possible problem to manage. This is what it means to operate at interstellar distances, not the romance of it, the reach, the achievement, the operational reality, which is that a team in a building in Pasadena sends a command they have checked and simulated and verified to the best of their ability, and then they wait. They cannot watch it happen. They cannot intervene if something goes wrong mid-procedure. They can only have prepared well enough that intervention is not necessary, and then they can wait, and the spacecraft will either survive it or it will not. Badarudin has said the team has gotten accustomed to this rhythm. The delay used to be a small time delay. It has gradually gotten longer and longer over the years. The engineers who work on this mission have built their professional practice around a communication architecture that has no equivalent anywhere else in operational spaceflight. They write commands they will not see executed. They receive confirmations of procedures that ended a day ago. They manage a spacecraft whose present they can only ever know as the past. The command will be sent. The team will wait. The result will arrive 23 hours after the spacecraft knows it. The signal that arrives from Voyager 1 is less than 1/1,000,000th of a watt. Put that number next to something familiar and the comparison does not quite work, because nothing familiar operates at that scale. A smartphone's Wi-Fi radio transmits at roughly 100 milliwatts, 1/10th of a watt, when searching for a network. The signal arriving from Voyager 1 is 10 billion times weaker than that. A single human cell generates on the order of 1 picowatt of heat, 1/1,000,000th of a watt, just from its ordinary metabolic activity. The signal from Voyager 1, after traveling 15 billion miles, arrives at the antenna of a deep space network dish, carrying approximately the same energy as the heat produced by a single living cell, doing nothing more than existing. That is what 23 watts looks like after crossing 15 billion miles of space. The 23 watts is itself worth understanding. The spacecraft's radio transmitter, the device that takes the science data and engineering telemetry assembled by the flight computer and converts it into an electromagnetic signal aimed at Earth, draws 23 watts of the spacecraft's total available power. 23 watts out of roughly 200. More than 10% of the entire power budget of a spacecraft that has been carefully rationing every watt for years goes to maintaining the communication link. Not to science, not to keeping the fuel lines warm, to the transmitter and the systems that support it. Because without the transmitter, nothing else the spacecraft does reaches anyone. The transmitter has been running since 1977. There is no backup transmitter that can be switched on if it fails. The redundant systems that existed on the spacecraft have been progressively taken offline over the years as their power demands exceeded what the budget could support. What remains is the primary transmitter and the S-band emergency backup, and the S-band, as the 2024 annealing attempt demonstrated, is useful only as a carrier signal, a presence detector, rather than a data link. The primary transmitter is the mission. If it fails, the mission ends that day, regardless of the power budget, regardless of the instruments, regardless of the Big Bang. In 1977, 23 watts out of 470 was less than 5% of the power budget. Today, 23 watts out of roughly 200 is more than 10%. The transmitter is consuming an ever larger share of a resource that is not being replenished, and at some point the arithmetic of that relationship will become the binding constraint on the mission, regardless of what happens with the instruments and the heaters and the Big Bang. The deep space network that receives those 23 transmitted watts, attenuated to 1/1,000,000th of a watt after their journey, is itself a system with its own constraints and timeline. The network operates 3 complexes, each housing multiple dish antennas of various sizes, positioned at roughly 120-degree intervals around the Earth to ensure continuous coverage as the planet rotates. The largest dishes, 70 meters in diameter, are the only ones sensitive enough to maintain a reliable data link with the Voyager spacecraft at their current distances. 70 meters is the length of roughly half a football field, translated into a parabolic surface that must be pointed at a target whose angular position in the sky is known to extraordinary precision, but whose location cannot be directly observed. The reason the Deep Space Network can receive a signal at 1/1,000,000th of a watt at all is a combination of antenna physics and receiver engineering refined over 60 years of deep space communication. The large dish concentrates the incoming electromagnetic energy onto a receiver at its focus, the way a parabolic mirror concentrates light. The larger the dish, the more energy it collects. The receiver at that focus must add as little noise as possible during amplification, because at signal levels of 1/1,000,000th of a watt, the thermal noise generated by the amplifier's own electronics can overwhelm the signal if not carefully managed. The amplifiers used for Voyager reception are cooled to temperatures close to absolute zero specifically to reduce this thermal noise. The engineering that makes it possible to hear a 23-watt transmitter from 15 billion miles away is not just the large dish. It is the large dish combined with a cryogenically cooled amplifier combined with precisely calibrated signal processing, combined with a known frequency and a known polarization, and a known modulation scheme that has not changed since 1977. That last point carries weight. The signal from Voyager 1 has been using the same frequency, the same polarization, the same modulation scheme since launch. The Deep Space Network knows exactly what it is looking for. It is not searching for an unknown signal in an unknown format. It is tracking a specific, characterized, known transmission from a specific, tracked, predictable source, and it has been doing so for 48 years. The infrastructure of knowledge and calibration built up around that signal is itself a kind of resource, one that took decades to accumulate and that cannot be rebuilt quickly if it is lost. High data rate support from the current Deep Space Network configuration is projected to end around 2027 or 2028. After that point, the data rates achievable with Voyager's declining power and increasing distance will fall below what the standard network configurations can handle efficiently. The team will need to adapt further, possibly including the careful, closely modeled decision to shut off the Bay 1 heater that keeps the flight computer warm, freeing power for the digital tape recorder that stores science data before transmission. The models suggest it might be survivable. The annealing experience suggests it should be approached with caution. Every thermal trait on this spacecraft has already been made once. The ones that remain are the ones that were saved because they were harder. The end of the Voyager mission will not be an event in the way that a spacecraft failure is an event, a sudden cessation, a last data packet, a moment when the signal is present and then absent. The power decline is gradual. The signal will degrade before it disappears. As the available power to the transmitter decreases, through the slow decline of the REIT-G output, through the power demands of the systems that must be kept running to prevent the spacecraft from freezing or losing attitude control, the signal-to-noise ratio at the receiving dish will decrease. The data rate that can be supported will fall. The team will adapt, reducing the science data rate, using longer integration times at the dish to pull more signal out of the noise. At some point, the signal will fall below the threshold at which useful science data can be extracted. The mission may continue in a degraded form, tracking the carrier signal, monitoring the spacecraft's health through engineering telemetry at the lowest possible data rate, for some time after the science instruments are effectively silent. At some further point, the carrier signal itself will fall below the detection threshold of the network. That point will not be announced in advance. It will be approached from a direction visible on a graph of signal strength over time, and the team will know it is coming, and they will extract whatever they can for as long as they can, and then the signal will be indistinguishable from the background noise of the universe, and the mission will end. Not because the spacecraft stopped. The spacecraft will not stop. There is a list somewhere in Pasadena of the order in which the remaining instruments will be shut down. It is not a secret document. It is not classified or restricted or filed in a drawer that only certain people can open. It is a working document, the kind of operational planning artifact that every long-duration space mission produces, updated as conditions change, consulted when decisions need to be made, amended when the engineering reality diverges from the earlier predictions. The Voyager team produced it in collaboration, the science team, the engineering team, the project manager, the mission manager, people who understood the power budget, and people who understood what the data was worth, and people who had to reconcile those two things into a sequence that could be executed in the real world under real constraints, without the luxury of waiting for a better option. The list exists because the alternative is worse. Without a list, every shutdown becomes a negotiation conducted under pressure, with the power dropping and the clock running, and the people in the room arguing from positions shaped by the urgency of the moment, rather than the considered judgment of people with time to think. The list moves the negotiation to a time before the crisis. It means that when February 27 arrives, when the power drops during the roll maneuver, and the team has to decide what to shut down and when, the answer is already known. Not because the decision was easy, because the decision was made already, carefully by the same people who are now executing it, and executing a decision already made is different from making a decision under pressure. The list has been executing for years. The Plasma Science Instrument on Voyager 1, off. The Plasma Science Instrument on Voyager 2, off, in October 2024. The Cosmic Ray Subsystem on Voyager 1, off, February 25, 2025. The Low Energy Charged Particles Instrument on Voyager 2, off March 24, 2025. The Low Energy Charged Particles Instrument on Voyager 1, off April 17, 2026. Each line a decision made once, in a room with enough time to think, and then carried out on the date the arithmetic required. What remains on Voyager 1, the Plasma Wave Subsystem, the magnetometer. What remains on Voyager 2, the Cosmic Ray Subsystem, the magnetometer, the Plasma Wave Subsystem, one instrument more, because Voyager 2 has been managed on a slightly different timeline. Its power budget differing from Voyager 1's, in ways that have allowed it to keep one additional instrument running longer. The Cosmic Ray Subsystem on Voyager 2 is scheduled to be shut down in 2026. After that, Voyager 2 will be where Voyager 1 is now, 2 instruments, 2 clocks, 1 list still to finish. What is known is the direction. The instruments will go dark one by one. The spacecraft will eventually be running on its transmitter and its flight computer, and whatever heaters are still operating and nothing else. No science, no measurement, just the carrier signal reporting the spacecraft's continued existence to anyone still listening. Then, at some point after that, the carrier signal itself will begin to fade. Not sharply, gradually. The way something disappears when it has been getting smaller for so long that the final absence is not a moment but a threshold, reached and passed without ceremony. Badarudin has said he wants to stay on the mission until the final transmission. He said it in the same register in which he says everything about this work, direct, unornamented, without the performance of sentiment. He described Voyager 2 as the one that has been flying the longest, and Voyager 1 as the one farthest from Earth, and said they both have a claim to fame. He described them as essentially twins who live different lives and have different medical problems and different experiences. The analogy is the kind that comes from spending years with something, from knowing it well enough that the technical language starts to feel insufficient and the human language starts to feel accurate, even when it is applied to machines. The team that manages the Voyager mission today is small, not a skeleton crew, not an operation running on fumes and obligation, but small in the way that a mission 48 years past its design life is necessarily small, staffed at a level appropriate to what the mission currently needs, which is a group of people with deep specific expertise in systems that no one else in the world knows as well, doing work that cannot be transferred to someone new without a significant learning curve, on a timeline that does not accommodate significant learning curves. The people on this team carry knowledge that is not written down anywhere in complete form. The documents are incomplete. The simulators are good, but not perfect. The knowledge that bridges the gap between the documents and the spacecraft lives in the people who have been working on it long enough to understand where the gaps are. That knowledge will not last forever either. People retire. People move on. The mission will end before the team does. That is the plan, the intended sequence. But the margin between those two events is not unlimited, and the people on the team know it. There is a specific asymmetry at the center of this story that none of the technical details fully resolve. The Voyager spacecraft will outlast the Voyager mission by billions of years. The mission ends when the signal falls below the detection threshold. The spacecraft does not end. It continues. At 38,000 miles per hour, on a trajectory that takes it away from the solar system in the direction of the constellation Ophiuchus, it will travel for 40,000 years before it comes anywhere near another star. And even then, near is a relative term. The encounter will be a passage through the same general region of the galaxy, at a distance of roughly 1.7 light-years from a star called AC plus 793888, in approximately 40,000 years. No one alive today will be alive then. No one who will be alive then will know the spacecraft is coming. The documentation of the Voyager mission will almost certainly not survive in a form any living person 40,000 years from now can read. We do not know what will exist then. We know only that the spacecraft will still be traveling. The spacecraft will also be carrying its 3 radioisotope thermoelectric generators, still producing trace amounts of heat as the plutonium-238 continues its 88-year half-life decay, though by 40,000 years from now, the generators will have become inert metal cylinders. The spacecraft will be cold throughout. The hydrazine in the fuel tanks, if any remains, will have frozen long ago. The thrusters will be silent. The antenna will have drifted to whatever orientation it happened to occupy when the last attitude correction was made, pointing at nothing in particular, fixed in that position by the absence of any force to change it. The flight computer will still be there. The wiring will still be there. The instruments, shut down one by one over the years, the plasma science detectors, the cosmic ray telescopes, the low-energy charged particle sensors, the plasma wave antenna, the magnetometer will all still be there, attached to the spacecraft, cold and inert and intact, traveling through interstellar space at 38,000 miles per hour. Not working, not measuring anything. Simply present, the physical remains of a decision made in 1977 to build something and send it as far as it would go. The mission ends when the signal ends, not when the spacecraft ends. The spacecraft does not end. That gap between the mission and the spacecraft, between the human event and the physical one, is the specific thing this story is about. Underneath the power budgets and the instrument shutdowns and the Big Bang maneuver and the list being executed in Pasadena, the gap is not a tragedy. It is not a triumph. It is a fact about the difference between what humans can build and what humans can maintain, and about the point at which those two things diverge. The spacecraft will outlast every person currently alive. It will outlast their children and their grandchildren and every generation for which the names of the people now working in Pasadena are remembered as anything other than entries in a historical record. Badarudin wants to be there for the final transmission. The team is trying to ensure that the final transmission is as far in the future as the physics will allow. They are doing this with a Big Bang maneuver they have not yet attempted, a thruster software modification they have not yet written, documentation typed on typewriters before the personal computer existed, and a communication link carrying 1/1,000,000,000 of a watt of signal across 15 billion miles of interstellar space. They are doing it because the data is still coming, because the plasma wave subsystem is still listening to the interstellar medium, and the magnetometer is still measuring its magnetic field, and no other instrument anywhere in the solar system is in a position to make those measurements, and every day those instruments stay on is a day of data that would not otherwise exist. They are doing it because the list is not finished. The spacecraft will keep going. It just won't be talking to anyone. The signal that arrives from Voyager 1 is less than 1/1,000,000,000 of a watt. It is arriving right now. The dish in the Mojave Desert, or Madrid, or Canberra, whichever one is currently facing the right direction, is receiving it, amplifying it, decoding it, routing it to the operations team in Pasadena, who will look at the numbers and make their decisions, and send their commands, and wait their 23 hours. The thread is intact. The signal is present. The mission continues. Voyager does not know it is being listened to. It has never known. It transmits because that is what it was built to do, and it will keep transmitting after the last person who can hear it has logged off and driven home and left the building dark.